But in order to do that correctly, we have to get the currents simulated right. So here is an example from a data collection effort that happened in 2006 from Dana Passage. We don't have that many measurements of currents, but when we do, we are able to simulate currents well. These are time series from an ADCP station at 3 different levels in water column. And you can see that we match measured currents both in magnitude and in phase. So peaks, mean, and lows are matched up correctly. So this is at a specific station, and we do station comparison to obtain confidence in the model. And once we have the model working to a certain level, we are then able to use the power of the model to distribute the information all over the entire domain, and then do analysis such as tidal averaging and come up with patterns. So here you have 2 plots where I've averaged surface currents for an entire year from 2006. And we do that just to see how good the model is in reproducing certain features. On the top screen, we point out that there is a Strait of Juan de Fuca eddy near the mouth of entrance to Strait of Juan de Fuca. And that is a feature that comes right out of the model without us trying to tweak it out. It's been reported that this is a hard feature to reproduce, but seems to come out just fine. When you average the currents out, it jumps out. The other feature that we looked for as a result of a recent Salish Sea conference where professors from UBC showed some drogue results where they released drogues in front of the Fraser River mouth, and the drogues went in a circular motion. I think that study was in connection with the outfall sighting analysis. And we looked at that spot. It shows in the Fraser River eddy. I don't know that that's the name, but I just wrote that down like that. Shows up quite well. Okay? So this is just for us to get a good feel that the model is reproducing hydrodynamics as they occur. And there is a very important, before I do that, there is an animation. And I think this is just an animation that we produce to show that we can refine regions near regions of complex shoreline, and then generate currents to simulate tidal flushing. And also, I know Carol is here today, and they do kayaking. There's some sort of a sailboat race that happens around San Juan Islands, and folks were interested in getting this information. So it was generated at that time, and I just provided to them. So some fun exercises that you can do with the model. But having access to this information also allows us to compute some really important circulation, quantitative circulation information. Christopher Krebs mentioned, nutrient fluxes. They are tied to amount of water that comes in from ocean. The plot on the top is a transect that goes from left to right. It's a transect that goes from entrance of Strait of Juan de Fuca all the way to South Sound. And it shows how water moves into Puget Sound from the bottom. The water moves in Pacific Ocean, water moves in after averaging out the tides, goes over Admiralty Inlet, and goes into Central Sound, upwells, and comes back up to the surface, and then the surface water moves out. And so these numbers, when we computed, a very interesting number came out. You know how everybody thinks that the water comes in from Pacific Ocean, and then it mixes with surface water and goes out. But there is an important feature that happens at the Admiralty Inlet sill. There is a downwelling that happens that is shown as the number R. Can't point. It's right in the middle where it says Puget Sound Basin, and it shows downwelling. So computed numbers from the model show that nearly 60% of the outflow water is recirculated back into Puget Sound. And that has implications to what we discharge to Puget Sound and how we view what happens to water that is discharged to Puget Sound. It doesn't just go out. 60% of the water we computed, thank you, it comes right back to Puget Sound and mixes. Right? And this is not a new thing. There is a paper by Ebsmeyer in 1984 where they computed the same thing just using salinity measurements and numerical drogue study measurements, and their computed number was 2/3 of the water refluxes back into Puget Sound. And we just forgot, but now we are reminded again as a result of the model. So this is a new, I guess, memory recall or whatever you want to call it, refreshing our memory of our understanding of Puget Sound. Moving on to biogeochemical model, we decided to couple our hydrodynamic model to the biogeochemical model that's been used in Chesapeake Bay. Our Puget Sound is not Chesapeake Bay, we know that, but no reason not to learn from the experience that they have gained over 30 years. So we have coupled hydrodynamic model to kinetics that have been developed over 30 years of time in Chesapeake Bay. The model is called C=ICM, and we have connected it up to our FVCOM model. We call it FVCOM ICM, and that is part of our Salish Sea modeling system. It generates algae growth and die-off. In the morning, we saw algae measurements. So the model simulates diatom bloom early in the summer, then die-off, and then a summer growth, and then once again a die-off towards the end. Oops. Okay, really fast. I will go through. So the model simulates corresponding withdrawal of nutrients followed by prediction of DO. We managed to incorporate sediment diagenesis. As a result of sediment diagenesis, we are able to connect up die-off of algae and their settling to sediment and decay of algae in sediment. Only with that connection to sediments completed, we are able to simulate depletion of DO all the way to hypoxic levels in Puget Sound. And I should mention, and it's been mentioned before, in its current state, we have the carbonate chemistry and ability to simulate pH. And for folks who are interested, we can provide numerical statistics of model skill, but I think I'll stop here and hand it off to Anise. Thank you.
All right, so the whole morning we have heard this word residence times several times, right? We have heard it in Bart Christian's presentation. He was trying to link residence times to the declining eelgrass areas. We've also heard it during Christopher's presentation and also in Sandy's presentation linking residence times to the health of benthos. So my presentation is about residence times in Salish Sea. So a very basic definition of residence times is how long a mass of water stays at a certain location. So the longer the residence times, there is more potential for pollutant buildup. And there's also more potential for increased productivity and also depletion of nutrients. There's also oxidation of ammonia to nitrate, or something we call as nitrification. And when the algae settle down, there's more potential for algae to settle down. There's more time for algae to settle down, and more time for the dead algae to decompose and deplete oxygen. So knowing this, the residence time, I guess, of the entire Salish Sea can tell us where the hotspots are or where the biogeochemical stressors are. Okay. So you have seen this plot in Sandy's presentation. This plot was developed by Skip Albertson of Marine Unit, and he basically used 4 stations, as you can see in that map, with those red dots, and he used observed data, and using salt balance, I guess, he created this plot, and those dots are residence times for individual years, and the line is a running 16-year average residence time. And so those dots show, that in any particular year, how the residence time deviates from that average. And I will be basically focusing on 2006 and 2014. I think in Sandy's talk, it was 2006 and 2008. Just want to point out that a Washington Shellfish Institute Blue Ribbon Panel on Ocean Acidification, this is a report that came up in 2012, and they recognize the importance of residence time. They're saying that what is not known is the magnitude of the effect that the anthropogenic nitrogen inputs have on pH. Now, since that time, I think Greg is going to show that we have made quite a leap, I guess, in coming up, in linking the pH with the anthropogenic nutrients. But they also mention here that understanding, the impacts of anthropogenic nutrient sources on pH will require new knowledge of residence times. And in the bottom, they say basins with strong stratification and long residence times should be the most susceptible to land-based and human sourced inputs of nitrogen. So the importance of residence times is recognized, I guess, by this panel. All right, so in estimating the residence time, we use something called the E-folding time. So what we do is we use this Salish Sea Model that was developed by PNNL in collaboration with Ecology, and we input a initial virtual dye throughout the domain, and then we take a vertical average of every grid cell, is a vertically averaged dye concentration of every grid cell, and we generate a time series, and the time it takes to reduce the initial concentration by 37% is the E-folding time. And why we call it E-folding time is because 0.37 is 1 over the base of natural logarithm. I guess this is what the scientists have been traditionally using. So that's why they call it the E-folding time. All right. So here is a map of residence times from 2006. And the legend here is the E-folding time in days. So if it is dark blue, it is 0 days. So it is the flushing times or the residence times is 0 days. And if it is deep yellow, it is 350 days, meaning that it takes 350 days for initial dye concentration to reduce it down to 0.37 of its initial value. And as you can see, no surprises. Lynch Cove, Hood Canal, South Sound, and Woodby Basin have the longest residence times. And it's interesting what Bart pointed out. There are declining eelgrass areas in Lynch Cove and South Sound. Now, this is very interesting. In 2014, all of a sudden we find that the residence times have gone down, which means that the dye is getting flushed out faster from the system. So we'll explore that a bit, why that is. So in this slide, I'm showing that if you take the whole Salish Sea and do a volume-weighted average of the dye, so you generate a single time series for the whole domain. The first row there says that the Salish Sea residence times goes down from 160 days in 2006 to 54 days in 2014. And then you have other regions there showing a similar trend. Just to take an example, I guess South and Central Basin, which is the dark red colored area, goes from 249 days to 165 days. And again, this is because what I think Christopher alluded to is basically the effect of estuarine circulation. When you have low fresh water in the system, then the estuarine circulation slows down. When you have high freshwater flows, there is a speedy estuarine transport. As a result, you have faster or shorter residence times. So here you can see that in 2006, Fraser River annual average flow is roughly around 2,180 cubic meters per second. In 2014, it jumped by almost 1,000 cubic meters per second, and that's what is, increasing the estuarine circulation in the system and reducing the residence time. This diagram, I guess, on the right, basically shows that that the ocean water comes in at the bottom. I think Tarang mentioned that. And on the surface, you have the fresh water going seaward. Bottom, you have the seawater coming landward. So you have this conveyor belt, I guess. And when you have more freshwater flows, faster is the conveyor belt. And also to see this, I have a transect, a thalweg transect from Lynch Cove all the way to Nia Bay. It's a vertical transect, and I have an animation that shows this. So as you can see that so on the right is Nia Bay, on the left is Lynch Cove, and the middle is the Admiralty Inlet sill. And as you can see, the water is coming from the ocean in the bottom, and it goes over the sill. And you can also see near Lynch Cove, the water is turning slightly blue, and that is Skokomish River trying to dilute the dye. And as you can also see, the bottom of Lynch Cove, nothing is really happening there. And so that, again, points to the fact that Lynch Cove has a long residence time. So this is basically taking the e-folding time for the bottom layer on the left and the top layer on the right. And this kind of, makes me think that, well, the top layer, has longer residence times than the bottom. But again, this is the topmost layer in the model. I didn't really average out the dye concentrations above the point of no motion. This is just the top layer and the bottom layer. But it does point to the fact that the bottom layer, dilutes things faster, as you saw in the animation by the ocean water. So in the conclusion, longer residence times occur in remote inlets and trapped basins. In general, longer residence times occur for surface waters compared to bottom waters. I think that's a generalization. It's not true everywhere. Longer residence times occur with poor estuarine circulation with low freshwater flows. We can now use the Salish Sea Model as a tool to quantify residence times for any portion of the model domain or year. Residence time maps show us areas that are susceptible to biogeochemical stressors and can be made available to the scientific community. Thank you.